So we're going to do some more with curves sketching in this video. One of the main things in this video we'll look at is the slant asymptote. So the slant asymptote is an asymptote where the graph goes along it and gets as large or as small as need be. For any rational function, we get a slant asymptote, as we mentioned in the last video, when the degree of the numerator is one more than the degree of the denominator. We can find the slant asymptote by either using synthetic division or long division. Anytime the denominator is linear, we can use synthetic division. And you should have seen this in your rational functions unit in pre-calc. To do synthetic division, outside the box, you will put whatever makes the denominator 0. So in this case, we'll have a positive 1. The whole idea of synthetic division, which makes it easier, is you're only working with coefficients rather than the variables as well. Inside the box, we will put our coefficients. So we'll start out with a -3 because that is our coefficient of the x squared. Now it's important, if there's any terms missing, you have to hold that spot with a 0. Well, after an x squared should come a plain old x. We don't have a plain old x. That means we must have 0 x's. So we have to hold that spot with a 0. And then our constant is a 2. So again, our setup, the number outside came from what makes the denominator 0. Inside, it's each of our coefficients, okay, spaced out. And if a term is missing, you need to hold that spot with a 0. Once you have this, the first thing you always do is just drop down the first number. Then you multiply that -3 in the green with the 1 that's on the outside and put your answer here. So we get a -3. And then you always add. So we're going to do 0 plus a -3 gives us a -3. And then we'll just keep repeating that process. So we'll do this new -3 times the 1, which happens to give us -3 again. And now we'll add. 2 times -3 is -1. Now, for your answer, these are the coefficients of our answer. Your degree of your answer is always 1 less than the degree that you started with. We started with an x squared, so we'll start with a plain old x. So we'll have -3x minus 3, and you might remember from last year, this is now -1 over x minus 1. Well, we're looking for, in our horizontal asymptotes, what happens when we get really, really large x values. Well, this part here, when x gets huge, you'll have 1 over a huge number. That's going to get closer and closer to 0. So that is going to have very little effect on our slant asymptote at all. So you ignore the remainder. Therefore, our equation of our slant asymptote will just be y equals our linear part, -3x minus 3. For the next one, our number outside will be a 2, because that's what would make the denominator 0. Inside, we'll have a 1, a 3, and a 2. We weren't missing any terms. You don't have to hold any spots with 0. First thing we always do is drop our first number down, which is 1. That'll multiply with the number on the outside. 1 times 2 is 2, and that'll go here. We always add. That'll give us 5. Then we'll multiply the 5 with the 2 that's outside the box, so we get 10. Add them, and you get 12. So this is really x plus 5, and remember we ignore our remainder. So you just have y equals x plus 5. And again, the reason we ignore the remainder is because as x gets huge, that's going to go to 0. So it's not going to really have an influence as we have really large x values. Now the last one, the denominator is not linear. So unfortunately, we cannot use synthetic division. We'll have to use long division. Inside goes the part in our numerator. And just like before, we've got to hold our spot anytime there's a missing term. Notice the x is missing, so we'll have to hold that with a 0x in this spot. So we'll have 2x cubed plus 4x squared plus 0x minus 9. And on the outside goes our denominator. Now, it's usually easiest to have it in standard form where the largest exponent comes first, so I'm going to write it as negative x squared plus 3. Now, we want to figure out what's going to go in our division right above the 2x cubed. So we need to ask ourselves, what times a negative x squared will give us the 2x cubed? Well, in order to get that, we would need a negative x. So in other words, negative 2x. So in other words, you're trying to multiply with your part outside to match up with the first term underneath the division sign. So now we'll take this negative 2x and multiply it by the negative x squared plus 3, giving us 2x cubed minus 6x. Now actually, I got to write that minus 6x in a different spot just so it's lined up. We're going to move the negative 6x and put it over there so it's lined up under the x's. Now when you're doing log division, you then subtract. 2x cubed minus 2x cubed, that goes away. 4x squared minus nothing in that spot is just 4x squared. 0x minus a negative 6x, that becomes a plus 6x. And then negative 9 minus nothing under the constant, so that's still just negative 9. So our next question is, we'll ask what times negative x squared will give us a positive 4x squared? Well, that'll just be a negative 4. Negative 4 times negative x squared will give us 4x squared. Negative 4 times 3 will give us negative 12. We'll line that up under the 9. We'll now subtract. Those will go away. 6x minus nothing is 6x. Negative 9 minus a negative 12, that'll become a plus 12, so we get plus 3. And now we'll ask, what times negative x squared gives us 6x? Well, there's nothing. Our degree is too small because it's just 6x. So this would really be our remainder if we had it. We would have a 6x plus 3 over negative x squared plus 3. But remember, we ignore our remainder, so we're all set. Our slant asymptote, therefore, is y equals negative 2x minus 4. So we talked about this in the last video, but just in case you wanted a nice chart, these are the 4 different possibilities for horizontal asymptotes. The first one, if the degree of the bottom is smaller than the degree of the top, it's just always y equals 0. I think that one was 4th when I had listed it on the previous video. If the coefficients are the same, it's just the ratio of the leading coefficient. So in this case, 2 over 3, so you get y equals 2/3. I believe that was the first one listed on yesterday's video. If the top degree is 1 more than the bottom, then that's when you do division. That will give you a slant asymptote. And the last case, when the numerator degree is more than 1 greater than the denominator degree, then there's just no horizontal asymptotes. So we're going to look at 2 graphing examples like we did on the last video, carry them all the way through. First one here, x cubed over x squared plus 1. We've got to first check the domain. Well, we've got a rational function, so we want to see when is the denominator going to be 0. Well, that would mean x squared would have to be a negative 1. When you square something, it comes back positive, so there's no way to make the denominator 0, so therefore our domain is all real numbers. Next, we'll start out with our y-intercept. We'll put 0 in for x and see what you get back. Well, you get 0 over 0 plus 1, which is just 0. Well, that means that's automatically an x-intercept, and because that's the only thing that will make the numerator 0, that's our only x-intercept. Next, we need to check symmetry. When we plug in a negative x, that will become negative x cubed over positive x squared plus 1. That is the same as if we had just negated our original function. Therefore, this is odd, and it's symmetric with the origin. What this means is, once we graph it, if we turn it 180 degrees, it should look exactly the same. So that's kind of a little check that you can use. Because there was nothing that made our denominator 0, there were no vertical asymptotes. For a horizontal asymptote, our degree of the numerator is 1 more than the degree of the denominator, so therefore we are going to have a slant asymptote. Because the denominator is not linear, we'll have to use polynomial long division like we just did. So, on the inside we'll just cubed, on the outside we'll have x squared plus 1. So we want to know what times x squared will give us x cubed. Well, that's just x. So that'll give us x cubed plus x. When we subtract, we'll just get a negative x. Well, now nothing times x squared gives us negative x, so that's it. So our asymptote is just going to be y equals x for our slant asymptote. Next, we'll do our first derivative. We've got low d high, so x squared plus 1 times 3x squared, minus high d low, so x cubed over 2x, or times 2x, all over x squared plus 1 squared. We'll neaten that up a bit. We'll have 3x to the 4th plus 3x squared minus 2x to the 4th. So, and that'll all be over our x squared plus 1 squared. And when we simplify the top, we'll get x to the 4th plus 3x squared over x squared plus 1 squared. So we saw before that nothing will make the denominator 0, so there's nothing where it will be undefined. The numerator, when we set that equal to 0, we can pull out an x squared, and we're left with x squared plus 3. So this will give us x equals 0. This will be x squared equals negative 3 when we subtract it over, or x is equal to plus and minus square root of negative 3. It's imaginary, so we'll get nothing from that. So 0 is the only critical number on our number line. To the left are negative numbers. We'll notice everywhere we have an x, it's an even exponent, meaning it'll come back positive everywhere. And to the right, positives, when you plug them in, will also come back positive. So we will be increasing from negative infinity to 0. The union of that was 0 to infinity. Because it goes plus to plus, there are no mins or maxes. Next up, we'll find the second derivative. So we'll have f double prime x. We'll do low d high. So we'll have x squared plus 1 squared times 4x cubed plus 6x minus high d low, so x to the 4th plus 3x squared. Derivative of the bottom will have a 2 out front. It'll become x squared plus 1 to the 1st times 2x. And that's all over x squared plus 1 to the 4th. Remember, second derivative of a rational function almost always will have something that'll cancel out in every term. In this case, everything has an x squared plus 1, so we can take one of them away. And now we'll simplify. That first thing we're going to have to FOIL. So we'll have 4x to the 5th plus 6x cubed plus 4x cubed plus 6x. To the right, we have a 4x on the far right and the negative in the middle. So we're really distributing a negative 4x to that parenthesis. So we'll have negative 4x to the fifth, negative 12x cubed. And this is all over x squared plus 1 to the third. If we neaten this up, the x to the fifth add to 0. The x cubed, we have negative 2. And then we've got a plus 6x. And we want to know, when is that equal to 0? Well, remember we said there's nothing that will make the denominator 0, so nothing that will make it undefined. We have to set the numerator equal to 0, because the numerator is what makes a fraction equal to 0. We'll get negative 2x equals negative 6. That's x cubed equals 3. So x will equal the cubed root of 3. Something's off here. It looks like I forgot an x. So actually this is going to switch a little bit. That was a plus 6x, sorry. So because that's a plus 6x, we can pull a negative 2x out. We're left with positive x squared minus 3. So now when we set equal to 0, we'll get x equals 0. We'll get x squared equals 3, so x will be equal to plus and minus square root of 3. So we actually get 3 values we're going to put on our number line this time. Now you may say, we don't know what square root of 3 is without our calculators. Well, A, you can have a scientific calculator if you want, or just know what's in between the perfect squares. 1 and 4 are perfect squares. Square root of 1 is 1, square root of 4 is 2, so square root of 3 is somewhere in between 1 and 2. A little more precisely, it's about 1.7 or so. It's important to note that our denominator, the x squared plus 1 cubed, must always be positive, because when you square something, it'll be positive, then you're adding a 1. So that's not going to affect our sign at all. If we take something like negative 10 million, negative 10 million cubed is a really large negative number, times negative 2 is a really large positive number. Negative 10 million times 6 will be a negative, but not nearly as large as that first part, so therefore this will come back positive. If we take something like negative 1, that's nice and easy to plug in. The first part will come back as a positive 2, and then a negative 6, so we'll have a negative. If you put in a positive 1, we'll have a negative 2 and a positive 6, so that'll be a positive. And if you put in like positive 10 million, it'll be negative 2 times positive 10 million cubed, which will be a huge negative number. And then 6 times 10 million will be big, but not quite as big as the first part, so it will be negative. Therefore, we are concave up from negative infinity to negative square root of 3, the union of that with 0 to square root of 3. And we are concave down from square root of 3 to 0, the union of that with, negative square root of 3 to 0, the union of that with square root of 3 to infinity. Our inflection points we change from positive to negative and negative to positive at each of them. So we will have negative square root of 3 comma something. We'll have 0 comma something. And we'll have square root of 3 comma something. Well, the 0 should be the easy one, because we know 0, 0 is our intercept. Now, if we think of our original function, we had f of x equals x cubed over x squared plus 1. Let's work with the positive square root of 3 first. That might be a little bit easier. That'll be square root of 3 to the third over square root of 3 squared plus 1. Well, on the bottom, that'll just be 3 plus 1, which is 4. And square root of 3 cubed is like saying square root of 3 squared times another square root of 3. So that'll be 3 square root of 3 over 4. Now, the only difference with the negative is the numerator will be negative in the other one, so that will just be a negative 3 square root of 3 over 4. So now we are ready to sketch our graph. Okay, this was a bit messy. The ones with a slant asymptote usually are. Our slant asymptote was at y equals x, which that goes through points like 1, 1, 2, 2, 3, 3, 4, 4, and so forth. We have an inflection point at 0, 0. We have an inflection point at negative square root of 3, comma, negative 3/4 square root of 3. Well, the key is we have to decide which side of the asymptote that's going to be on. Well, the point that should be on the line is negative square root of 3, comma, negative square root of 3. Well, if you're taking 3/4 of a square root of 3, it's something smaller than that. So that's got to be on the side of the line going towards the x-axis. Same thing with our positive square root of 3. That's got to be on the side towards the x-axis. We did not have any maxes or mins, so we don't have to worry about that. And now we'll just work with our concave up, concave down. Now keep in mind, as you go to the far left and far right, it's got to approach the asymptote. And horizontal or slant asymptotes, it could potentially go through. Horizontals, it's okay to go through sometimes. Vertical, you cannot. So we're concave up from negative infinity to negative square root of 3. So we'll be along the asymptote and kind of just come towards our inflection point like that. Then we'll be concave down, so we'll look something like that. Then we're back to concave up, looking something like this. And then we're back to concave down, where it will approach the asymptote. Here's a nicer version of it. And you can see those inflection points there, and our slant asymptote the same as what we found. We'll look at one more example where we're going to graph the whole thing. Natural log of 4 minus x squared. We'll start out with our domain. Well, in a log, the inside needs to be positive. So this is saying that 4 minus x squared has to be greater than 0, because it has to be positive. Well, if we factor that out, that's 2 plus x, and 2 minus x has to be greater than 0. Our key numbers are at negative 2 and 2 when we put them on a number line. You did a lot of these in trig, the first half of trig. We'll have open circles because it's a greater than. When you plug in something like negative 10, you'll get a negative times a positive, which is a negative. When you plug in something like 0, you'll get 2 times 2, which is a positive. And when you plug in something like 10, you'll get a positive times a negative, which is a negative. Well, we wanted it to be greater than 0, so the section that will work is the part in the middle. This means our domain is going to be that x is greater than negative 2, but less than positive 2. So only at those sections will it exist. Now, because of that, that means at negative 2 and positive 2, you can think of it almost like a barrier, there will be asymptotes that will exist. Our concave up and concave down will tell us whether that should be going down or up along those asymptotes. Next, we have our intercepts. So your y-intercept, you just put in 0 for x. So that's 0, comma, natural log of 4. Next, we'll have our x-intercepts. We'll want to know when this is going to be 0. So we'll have 0 equals natural log of 4 minus x squared. We're going to have to switch forms. Natural log is really log base e, so this will be e to the 0 equals 4 minus x squared. E to the 0 is just 1. Subtract your 4 over, you get negative 3 equals negative x squared. That's 3 equals x squared, so x will equal plus and minus square root of 3. So our x-intercepts will be negative 3 comma 0, the square root of 3 comma 0. Now your symmetry is going to be even because when you plug in a negative x, it comes back as a positive x squared, so it's like nothing changed. Our asymptotes, because negative 2 and 2 is where it's cut off, where it's defined, we'll have vertical asymptotes at each of those. And now we have to take the derivative. Well, remember, a natural log's derivative is derivative of the inside over the inside. Oops, we have y, not f of x. So just so we can see it down here, we had natural log of 4 minus x squared. Derivative of the inside would be negative 2x over the inside of 4 minus x squared. On our number line, we'll first see, are there any values that will make it undefined? Well, that would be 2 and negative 2. Then is there anything that makes the numerator 0? Because that's where a fraction would be 0, and that's when x is 0. So we have 4 gaps to check. When you put in a huge negative number, like negative 10 million, the top will be positive. You'll have 4 minus a huge number, so that'll be negative. Positive divided by a negative is a negative. When you put negative 1 in, you get 2 on top, which is a positive. And on bottom, you'll get 4 minus 1, which is a positive. Positive over a positive is a positive. When you put in positive 1, you'll get negative 2 over 3. So a negative over a positive is a negative. And when you put in a huge positive number like 10 million, you'll get a negative on top. You'll get 4 minus a huge number on bottom. So that's a negative. Negative divided by negative is a positive. This means we will be increasing from negative 2 to 0. And actually, we had an error in what I was plugging in. Because keep in mind, anything outside the negative 2 to 2 is not going to exist when we're inside the log. So even though in this fraction it will happen, we actually don't have to worry about these parts because our function's not going to exist in those. So in fact, our only increasing spot is going to be from negative 2 to 0. Your decreasing is going to be from 0 to 2. That means when you go from increase to decrease, you'll have a max. Our max is going to be at 0 comma something. We know that's at natural log of 4. Now this is one where it would be helpful to have a scientific calculator, because I'm guessing most of you don't know what natural log of 4 is. Well, natural log of e is 1. That's like 2.73. Natural log 2 would be natural log of e squared. Well, 2.73 squared is going to be bigger than 4, meaning that natural log of 4 is somewhere between 1 and 2. And that's really all you need to know for graphing purposes. We'll now go ahead and take the second derivative. We've got a quotient here, so we'll do low d high minus high d low all over low, low. Distribute the negative 2, we'll get negative 8 plus 2x squared. You have a negative times a negative times a negative, so that'll be a negative, and it'll be 4x squared. So we'll end up, after we put our denominator in, we'll end up with negative 8 minus 2x squared all over our denominator, the 4 minus x squared squared. Our denominator is still 0 when we have negative 2 or 2. In the numerator, when we square something, it'll come back positive. Times the negative will be a negative. Negative 8 times a minus a negative will be negative. So the top is always negative. Notice the bottom is always positive because the whole thing's squared. So a negative over a positive is always a negative. So we're just going to always be concave down from negative 2 to 2. And remember, again, we don't care about the outside is because we found our domain was just the part in the middle. We are now ready to sketch this. We said we had vertical asymptotes from negative 2 to 2. Our graph is just going to be the part in the middle. We said our y-intercept was somewhere in between 1 and 2, and that was going to be a max. We have positive and negative square root of 3 for our x-intercepts. That's about 1.7. And we are concave down in this whole section, so we must look something like this. And here's a nice looking version of it. And that's all today for this video. We'll see you next class, period.